Hello and welcome. For this portion of the video and the following video, we should be going over different filter designs, me and Randall. We might actually do a Simulink workshop as well, but that'll be after this. But as of right now, we'll go over filter design within MATLAB and the essentials that we will need for filter design within MATLAB. So essentially, you would need to have the Bode function, which comes really handy when you're looking at the Bode plot for whatever filter design that you have, and its respective transfer function. So first of all, what you would need is the control systems toolbox. Now, if you go back to our previous installation videos, you'll see that we actually installed this with the add-on installer. But just in case that you haven't installed the control systems toolbox, or if you're not sure if you have it or not, what you could do is open up MATLAB and on the top three tabs, go to apps and click get more apps. Now, while this loads, you should just wait. It shouldn't take that long to load. As you can see, it loaded. So what you would want to do is click manage add-ons, and if you already have the control systems toolbox, you're pretty much set. But if you do not see this within your manage add-ons, just search for control systems toolbox within the search bar and actually install it. It should prompt you to close out of MATLAB and it'll actually install the whole toolbox. It shouldn't take that long, but after you are done doing that, you're pretty much set to follow along with this filter design. So when it comes to filter design and MATLAB, is usually you have to do more work on hand, and MATLAB is just used to confirm that all the values that you calculated and all the theoretical Bode plots that you have might have created are actually correct. It's a way of debugging yourself or your own work. It's just to check after yourself. So essentially, what you need to know for this is what transfer functions are, how to use transfer functions to actually find Bode plots, and how to implement that within MATLAB. We will be covering the last portion for actually knowing what transfer functions are and how you can actually create Bode plots off of these transfer functions based on whatever circuit you might have. You will go over this within EECE 311, hopefully, but I will go over it a tad bit with you guys, but I won't explain it too much because you will already be learning this within 311. So to start off, transfer function. So our first design filter that we will be making is a low pass filter. So we will be getting a transfer function for that low pass filter. And what a transfer function essentially is just a bunch of matrices, if you think about it, or a vector rather. So if you try to look back, we know that vectors are essentially polynomials. So, and within a transfer function, you have two polynomials, one in the numerator and one in the denominator. And you can set these polynomials as vectors and actually create the transfer function using the TF function right here, which actually sets trans equal to the transfer function of whatever numerator and denominator that you might have. And then trans can be used within the Bode function as well, alongside your omega or your time to frequency domain, which Randall should have covered, to actually create a Bode plot with the dB plot as well as the phase plot included. Now, well, you can use Bode numerator denominator without even using trans, but you can put it within the trans using the transfer function and put it within Bode to actually display the plot. But as of right now, we should essentially know what is needed to actually design a filter using MATLAB. So next we'll actually move on to the filter design portion of this video, which will be a low pass filter, a passive low pass filter. Now notice that this is a passive low pass filter and it is a RC circuit. It is not, it is gonna be a first order filter, as you can see right here, but I did not do this so that I could like have an easy explanation. Actually, I did do this so I can have an easy explanation. But later on within EEC 311, you'll be going over much more complex second order passive filters, which might be a RLC circuit, or you might actually be going through active filters as well, which also can be confirmed within MATLAB. But in our case, we're going to be working with this low pass passive filter right here. So as you can see, we have a RC circuit with a V in, V out, and two components, a resistor and a capacitor. Now, when it comes to designing filters, you have to assume certain variables. So for in our instance, we have to assume the cutoff frequency. So I'm just arbitrarily going to set the cutoff frequency equal to 5 kilohertz. Arbitrary, you can pick whatever you want. And since we have two different components, I also have to set one of these components arbitrarily equal to whatever I would want it to be equal to. So I can set the resistor equal to 1 kilo ohms. Again, completely arbitrary. You can set it equal to whatever you want, but this is when we actually have to use what we have learned within ECE 211, whether it be KVL, etc., to actually find the last component's value. And I'll do that with you guys right here. And this is, by the way, this is the transfer function for this circuit, but I'll be going that over this with you guys as well. So, in regards to this circuit, which is a low pass filter, to be more specific, a passive RC low pass filter, we have to think of it in the frequency domain. So, if you think about it, let's say in a DC way, where Vn would be a DC input, the capacitor would essentially become a short, but we are sending in a frequency, a certain frequency, a signal at a certain frequency, I should rather say. So the capacitor should be seen as a impedance. Or the resistor is already an impedance, but the capacitor should also be seen as an impedance. And when it comes to frequency domain, how the capacitor is seen is basically 1 over j omega c, where c is the value of the capacitance. Now, we have a j omega over here because we have a certain imaginary part to this capacitor, and we also have to include the frequency that we are sending the signal at. So I don't I shouldn't really get too deep into this. You will already learn this within whether it be EC 311 or 211 depending on your professor. So you should learn this regardless, but as of right now, just know that when we're looking at the circuit, the capacitor is essentially equal to 1 over j omega c. Now, we should also know some basic rules for KVL, anything. So let me start by just drawing a random circuit. So let's say we have a circuit like this, right? Where we have V in coming in, and we want to find V out over here, right? Maybe I should draw this a little bit better. Hmm. Excuse my drawing over here. So an easy way to find V out would be through voltage division. I'm pretty sure you guys should already know what voltage division is by now. But essentially what voltage division is let's say this is R1 and this is R2, right? So V out would be essentially equal to R2 over R1 plus R2 times V in times the voltage that is coming in. This is essentially voltage division, and this can be used with regards to this as well because we are seeing the capacitor as an impedance. So let me just get rid of all of this real quick, and then we'll basically do voltage division, but with the capacitor. So V out would be equal to R2, which in our case is the capacitor, so 1 over j omega c over R, which is going to be our R1 in this case, R plus 1 over j omega c times V in. Now, another thing that you need to know, which you should already know, hopefully, is that transfer function, so let's just say h of w, a transfer function is essentially equal to the V out. I really need to learn how to draw V out over V in. So we have our V out, we have a V in. All we have to do is just divide the V in over. So our actual transfer function essentially is just going to be 1 over j omega c over R plus 1 over j omega c. Now, you never really want this right here. So to simplify this, or rather, yeah, basically simplify, what we're going to do is basically just multiply j omega c to the whole thing. And this should in turn give us a final transfer function of 1 over j omega rc plus 1. Now, if you've looked at transfer functions, or if your professor chooses to do it this way, you would also see a h of s. So S essentially is just another way of saying JW. So S is basically equivalent to the imaginary omega. So we can essentially just change this to RC plus 1. This is essentially the same thing as the one above. So now that we know our transfer function, we can actually find the cutoff frequency, given that we know what the resistor and the capacitor is. But we only know what the resistor is, but we also know what the cutoff frequency is as well. So the equation based off of this, what the equation for the cutoff frequency essentially should be, is 1 over RC. Now, you see we have a omega here, which is rads per second, but our frequency that we chose previously, our FC, was 5 kilohertz, I'm pretty sure, yeah. It was 5 kilohertz, so we have to transfer this into this. So all we have to do is multiply by 2 pi. So 2 pi FC, need to write better, 2 pi FC would essentially be equal to 1 over RC. We also know our R as well. Remember, we set our R equal to 1 kilo ohms. So we essentially know everything within this aside from the capacitor. So we can just rewrite this using basic algebra and set the capacitor equal to 2 pi F 1 over 2 pi FC times RC. Maybe I should be. You get what I mean. And we know our values as well. So I'll write it out again neatly, hopefully. So essentially, it's just going to be 2 times pi times 5,000 times 1,000. Now you can calculate this with a calculator, but our capacitor at the end is gonna end up being 31.8 nanofarad. Now we know everything that is needed to essentially build the low pass filter. We can actually draw out a Bode plot for it right now as it is, but we will leave that to MATLAB to actually show you guys how MATLAB can be used to actually simulate the circuit to verify the different values that you have gotten. Again, MATLAB is again just a tool for verification. Or actually, Randall should also teach you guys how to do this same thing, but through Simulink as well, which should be a bit more. Sorry for a bit more beneficial to you guys. But as of right now, we'll just be confirming our stuff within MATLAB. So when you're working with, when you're actually trying to simulate a transfer function within MATLAB, you will have to clear all and close all. This is like essentially a starting. Oh, didn't mean to do that. Should probably start using my pen over here, but you have to clear all and close all, and after this you can declare your resistance value, which in our case was 1 kilo ohm, so 1000 over here, and you can declare your capacitor value as well, which is 31.8 nanofarad, so 10 to the negative 9. And this is our frequency domain right here. Randall should have gone over this, but I'll just touch it a little bit right now. So essentially what this says is that we're going to start at 0.1, we're going to increment by 0.1, and we're going to go all the way up to 1 times 10 to the 6. Now you see that I have very small incrementations. This will actually lead to the compiler taking quite a bit of time to actually compile this, which I don't mind, but if you want to have a faster compile, you can always decrease the step size or just start at 1, but decreasing the step size should work. Now that we also know that a transfer function essentially is just essentially is just two vectors, numerator and denominator, which are polynomials. In our case, the numerator was scalar, so we're just gonna have 1 over here, and the denominator was RCS plus 1, so we have RC and then 1 over here, since it's a first order polynomial. And taking these numerator and denominator vectors, or since numerator is a scalar, arrays, we can plug those into the transfer function and actually set trans equal to the transfer function. And this in further, this can actually go into the Bode plot as well. You take the trans and the frequency domain, enter it into the Bode function, and this should pop out a different tab with just the Bode plot itself. It should have a dB scale and a phase plot as well. What grid on over here does is it just displays the grid on the plot. So what I can do right now is I can go to editor and run. While we wait on it to compile the Bode plot, which it just did, as you can see, trans is going to be set to the transfer function that we actually found through our calculations. So as you can see right here, this is the transfer function. And now that we have sent it into the Bode plot, or the Bode function, we can actually see the Bode plot right here. This is the dB scale magnitude and the phase scale, or the phase plot. And as you can see, the characteristics do follow a low pass filter, and we can basically estimate that the cutoff frequency is around where we actually set it equal to. So it is accurate to a degree. And you can also simulate this through LT-Spice as well if you would like, but MATLAB usually does it for you, and you can actually confirm that everything that you have set up is correct, and that your filter works as designed. Now we'll actually cover more filter designs after this. We'll go over a passive high pass filter, passive band pass, passive band stop. We might go over all three, but maybe it's probably just going to be a band pass filter. But this should be really useful, especially if you are just going into ECE 311. You'll know how to actually design your own filter, and you'll know, or at least you'll learn the different methodologies that actually go into actually finding the transfer function and the the different component values as well. But for this video, it is kind of running over 10 minutes, so I will be stopping this video right here, and either me or Randall will pick up in the next video with another filter design. And we should be also sending out a video for not Symbol Lab, Simulink as well, uh, where we show you how to use Simulink within MATLAB. I'll actually open it up. We should have installed Simulink when we did the installation process, but if you, in any case, if you didn't install it, you can also install it from here. Simulink basically allows you to simulate anything, or in our case, circuits within MATLAB if you don't really want to use LT-Spice. But it is very useful later on, especially when you're working with DSP, digital signal processing. But as of right now, I will conclude this video.